Good morning, good afternoon, good evening, depending on the time you are receiving this video. I am Mr. Depayan, your chemistry teacher in the platform School for All. So today we are going to talk about synthetic routes. Okay, now the synthetic routes are subdivided into aliphatic and aromatic synthetic route. So today we are going to demystify those two concepts. So don't forget to like, to comment, to share, and put a click on the notification so that you are aware of the new updates. So going to aliphatic hydrocarbon, you will enter directly into our question 1. So in our question 1, what is this thing? Here we are saying that we study the synthetic route below and we need to answer the question that follows. So we are having a synthetic route in front of us. So now they are asking you in Roman 1, identify compound A, B, C, and E. So here we are asking you to analyze the different compounds and to identify the different compounds. So let us go through it. So if you go to compound A is having the general molecular formula C3H6. So when you see such a compound with the general formula C3H6, that is the number of hydrogen is directly equal to the number of carbon times 2. When you see already a compound like this, it means automatically that this compound is an alkene. This compound is an alkene. Read the general formula CnH2n. So whenever you see a compound in such of this form, it means that it's an alkene. Now, what if you see a compound in such a form? When you see a compound in such a form in which the number of hydrogen is more than the number of carbon times 2, automatically such a compound is what is an alkane with general formula CnH2n plus 2. And if you see a compound instead like this with C3H4, it means that the number of carbon, the number of hydrogen is less than the number of carbon times 2. So here we are instead having an alkyne and the general formula is CnH2n minus 2. So this is how we identify hydrocarbon based on their formula in synthetic route. So be very careful when you see a hydrocarbon. So by the side, if you're having a compound or an alkene with three carbon, surely the alkene is propene with the general formula or with the structure CH3, CH, double bond, CH2, and it is propene. So that is how you do to identify your compound A. Now for your compound B, you are having the general formula C3H7B. So whenever you see such a compound in which they say halogen, you directly think about haloal. You directly think about haloalkanes, where the number of hydrogen is more than the number of carbon times 2. And also there is a halogen, we think about haloalkanes. So haloalkane with general formula CnH2n plus 1x. Now, this haloalkane that we are seeing can have two possible structures coming from this my compound A. It can have two possible structures. It can be CH3, CHBr, CH3, or it can be CH3, CH2, CH2Br, in which this one will be the major and this one will be the minor product. Why is this one the major product? Because it is respecting what? Markov-Nikolson's rule, in which we have stated earlier in our previous video. So in this case, we are going to choose a structure, the major product. Okay, so in your synthetic route, always make sure that what you choose the major product, except there is the presence of an organic peroxide. If there is an organic peroxide, it is what anti-Markov-Nikolson It is antimicrobial. So make sure that there is no organic peroxide. But if there is one, you make sure that this one will now become your major product. So take note about compound C. Compound C is having the general formula C3H8O. So we analyze it. So when we see such a compound in which again the number of hydrogen is more than the number of carbon times 2, and there is one oxygen. So and there is one oxygen, automatically you will think about two homologous series. In this case, you can either think about alcohols, or you think about ethers because they are functional group isomers. So whenever you see such a compound, you think about two alcohols, or you think about ethers. Is it okay? Now, the alcohol, general formula of the alcohol is CnH2n plus 1OH, and the general formula of the ether CnH2n plus 2O. Are we together? But now, it means that if you're having these two possibilities, my two compounds can either be a CH3, CH2OH, that is for alcohol, or it can also be a CH3, CHOH, CH3. Now for the ether, it can only be CH3O, CH2, CH3. Now, based on the reactions we are having in our synthetic route, these ethers cannot be possible because the other type of reaction are not possible for ethers. So ethers, first of all, are not too reactive. Okay, so they are very unreactive. So we have very few types of reaction in which ethers will be involved. Now, in this case, we are dealing with what? With the alcohols. But now, which alcohol will be what? Will be our major product. Now, the alcohol we are going to choose the alcohol with respect to what? To our compound B. So if our compound B was this major product, automatically we are going to replace what the Br with what? With an OH. So it means that this one will be my major product in this case. This one will be my major product in this case. So compound C is propan 2-ol. Propan 2. Now, in compound E, we are having the general formula C3H6 with 1O. With 1O. So, look at it very well. When you are seeing that what the number of hydrogen is equal to the number of carbon times 2, and there is 1O, you will not think about alcohol and ether. In this case, you will think about aldehyde and ketones, which are also functional group isomers. Are we pleased? So the aldehyde, general formula CnH2n plus 1 CHO, whereas the ketone is CnH2n plus 2 CO. So now we are having such a compound. So what can be the structure? So here I can have CH3, CH2 CHO, which will be propanol, and I can also have CH3, CO, CH3, which is propanol or acetone. But now, which one are we going to choose here among the two? Now, we are going to see that what we are moving from compound C to compound E. So it means that we are first moving from the alcohol to what? To the carbonate. But our major alcohol was what? Was a secondary alcohol, if you identify it very well. So it means that what? We need to take a note on oxidation of alcohol. So I hope you know how to distinguish between primary, secondary, and tertiary alcohol. It is similar to primary, secondary, and tertiary halogenoalkane as we saw in the previous video. So yeah, I am having what? If I am having a primary alcohol and I perform what? An oxidation of the primary alcohol, I will produce what? An aldehyde. But now, if the oxidizing agent was in excess, I can further oxidize it to a carboxylic acid. But now, if I am having a secondary alcohol and I perform an oxidation reaction, what will happen? I will form a ketone. But now, with ketones, no further oxidation is possible. Now, if I was having now a tertiary alcohol, I will definitely have what? No oxidation, because the tertiary alcohol does not perform oxidation. So it is very important to know it. Now, if I was moving from what? From a secondary alcohol, I hope all of you are aware that it's a secondary alcohol here. This compound CH3, CH3 is a secondary alcohol. It's a secondary alcohol. So if I oxidize a secondary alcohol, what will I obtain? I will obtain a ketone. So that is why our compound E is what? Is propanone. So that is what was required for you for this first part of the question. I hope it is understood. So finally, we have concluded that our compound A is propene, compound B is 2-bromopropene, compound C is propan-2-ol, which is a secondary alcohol. And lastly, for compound E is what? Propanone or acetone. So now we go to the second part of the equation, in which they are asking you to identify the reagent X and Y. This one is very simple, as long as you already know which homologous series are there. So here I'm having alkene, which are converted to halogenoalkanes, and which are converted to we say it's an alcohol. So to convert an alkene to a halogenoalkane, we generally use a reagent which is what? X. X depends on what? On the halogen I am adding under reflux. So generally this reaction goes through in electrophilic addition mechanism. So you should go and exercise yourself in such a mechanism. Whereas to convert from my haloalkanes to my alcohol, what will I do? I will replace the halogen with OH now. So I will take, for example, a strong base like potassium hydroxide. I will still do it under what? Reflux. And now here the mechanism will be what? Will be in nucleophilic substitution mechanism. I will advise you to go and watch on those mechanisms. So it means that finally our compound is what? Propene. So it means that if I'm converting propene to 2-bromopropene, I will surely use what? Hydrogen bromide under reflux. And now to convert my 2-bromopropene to what? To my propan-2-ol, I will use the reagent potassium hydroxide under reflux. So the second part of the equation was very. We now go to the last part of our equation, in which they are asking you to give the physical changes which we observe when we are converting C to D and when we are converting what C to E. So let us start what we need from C to D. Now remember what C is, what is an alcohol. So this is C. Now to convert it to D, I put sodium. Now whenever an alcohol reacts with sodium, it will generally produce an alkoxide. And carboxylic with the release of what? Of hydrogen gas. It produces an alkoxide with the release of hydrogen gas. So in our case here, we are having what these alcohol CH3, CHOH, CH3, which was a secondary alcohol. Now when it reacts with what? With sodium. What will I obtain? I will obtain an alkoxide in which I will replace this hydrogen with a sodium atom. So I will have CH3, CH3, O sodium plus hydrogen gas. Now, what is the name of this compound? We generally call it sodium propan 2 oxide. So we call it pro-oxide. So propan 2 oxide. So this is what the molecule. But now, what is the observation we generally observe here? What is the observation we are having here? So the observation here, it is what? It's all about hydrogen. So there will be what? Effervescence or a gas will produce a pop sound with a lighted splint. So that is the test of what? Of hydrogen since ordinary level. Okay, so it means that here we are going to test for the gas that is evolved, and this is a physical test which occurs in what? Conversion of C to D. Now, if you go to the conversion of C to E, so in C we are having an alcohol, and we are placing what? Potassium permanganate, which is acidified to form a ketone. So with a very small, whenever you see this man or you see potassium dichromate, two of them are what? Are strong oxidizing agents that are involved in what? In oxidation. Now we saw the changes already, so it means I will move from my secondary alcohol to my ketone. But now what is the observation here? The observation here comes at the level of what? The potassium permanganate. What happens to the potassium permanganate? The purple potassium permanganate will be decolorized during what? During the reaction to manganese oxide. It's okay. So during the oxidation, he will be what? He will be reduced to manganese oxide, and the observation will be that purple color will disappear. So these are what the two observations that we are having in this question. So this is what for our question 1, that deals with what? The aliphatic synthetic code. So this question 1 is very simple for each and everyone to attain. Now we go to our second question, which has to do with aliphatic synthetic routes. We're now dealing with what? With nitrogenous compound. So we deal with the first form of synthetic route. We was talking about alkenes, alcohols, and haloalkanes. Now we have another group of synthetic route which is linking what? Nitrogenous compound. Now what is happening here? So first of all, we need to identify which homologous series does this compound belong to. So we go away to our principle. When you see that the number of carbon or the number of hydrogen is more than the number of carbon times 2, and there is an N. So we don't think twice. Here we are instead having what? An amine. Are we okay? So here we are having an amine, which is a primary amine. Whereas if you see such a person in a synthetic group, such a person will have a general formula C3H5N. You see that if you meet such a person in a synthetic group and you see that the number of hydrogen is less than the number of carbon times 2, it will not be an amine, it will be a nitride. So I hope you are seeing how to distinguish between amines and nitride in what? Alright, so here we have a primary amine. So surely the structure of this my primary amine will be CH3, CH2, CH2, to NH2, which is propylamine, So you see very well what happened. So immediately here I was having a carbon with no hydrogen. Now I am having these two hydrogen that have been added. So it means that what a powerful reduction took place, and of course we need a powerful reducing agent. So what happened here is that what I'll have a powerful reducing agent, which is lithium aluminum hydride in the presence of what? Of dry ether. So whenever you see that what there is a great reduction that took place, always think about what this powerful reducing agent. The next part, I'm converting a C, which is having the formula C4H7ONH2 to my compound A again, which you are already identified now. My compound A, which is CH3CH2Na2. Now, whenever you see such a compound, you don't stress, I don't panic, have it together. So you see that what the number of carbon is, the number of hydrogen is less than the number of carbon times 2, and then there is an N. Or let us say the number of hydrogen is more than the number of carbon times 2, because we consider hydrogen here. Okay, and there is an ON. Or whenever you see an ON, it is what? It is an imide. It is an imide. So here, the imide that can be formed, the primary imide, will be CH3, CH2, CH2, CONH2. So this is the imide functional group. Now, here we are converting from what form? Imide to amine. We are converting imide to amine. Now, to convert imide to amine, we are seeing that what this part resembles this part, but what is absent is what this CO. So it means that what I have removed this CO. Now, a reaction in which this CO is removed, this reaction is called Hoffman degradation. So Hoffman degradation. Now, what's the Hoffman degradation all about? So it is all about descending your homologous series. Defending the homologous series. So it means that if you were having 4 carbon atoms at first, you now move to 3 carbon atoms. So, and what is the reagent of Hoffman degradation? The reagent of Hoffman degradation is bromine in the presence of alcohol is formed like potassium hydroxide under reflux. So then I perform what my Hoffman degradation. You need to take a note that if I want to convert from an amide to an amine, in which there is no chain reduction, because it's possible. So in which there is no chain reduction, I will instead use the reagent lithium aluminum hydride with dry ether. So what I'm trying to explain here is that, for example, if I am having such an amide, which is propanamide, and I want to convert this propanamide to what? To propylamine. Without a reduction in what? In the chain, I will instead use this reagent. So take note about it. Hoffman degradation is what? Descending of the homologous series, whereas we have what? The use of lithium aluminum hydride, in which we are maintaining what? There is no reduction in the chain. Let us go to the next part of our synthetic route, in which we are converting again our A, which is CH3, CH2, NH2. Here we are converting now our A into a given compound D by passing through an acid chloride. Now, how can we identify our compound D? So whenever a primary amine reacts with an acid chloride, it will always form what we call an amide, which is what? A secondary amide. So what happens during the reaction? I'm having CH3, CH2, NH2, which combine with CH3, COCl to give CH3, CO, NH, CH2, CH3 plus HCl. N. So what actually happens in the reaction is that I will maintain this here. But now what will happen is that I am replacing this chlorine with one of the hydrogen, and now this part will come back here. So that is the principle. So here I am having propylamine, but now, and here I am having what? I am having ethanoyl chloride. Now, what is the name of this my compound that is from? I name it just like what? Like esters. So I start naming it. But now this alkyl group is attached to a nitrogen. So I will call it N-propyl. Propyl because I'm having 3 carbons here. N-propyl now because I'm having 2 carbons on this chain. I call it N-propyl amide. So that is the name of my compound D. That's the name of my compound D. Now, after we are converting compound A to a compound E and lastly to a compound F. So first of all, converting compound A into a compound E by passing through sodium nitrite and hydrochloric acid. So we call it what? The nitrous acid reagent. So whenever primary amine will react with such a reagent, I am going to release an alcohol with nitrogen gas. So it means that if I am having my primary amine, and I put this reagent, sodium nitrite in the presence of HCl, I am going to produce a corresponding alcohol, which is CH3, CH2O, OH plus a nitrogen gas which is generally released. So that is what is happening. So this is actually my compound. Now I'm having now the last step in which my compound E will be converted into a carboxylic acid CH3CH2COOH. So here we are having a primary alcohol. So my compound E is a primary alcohol. So to convert primary alcohol to carboxylic acid is very simple. We are going to use what? Excess potassium dichromate or excess potassium manganate, which is acidified in the presence of heat, and I will obtain my carboxylic acid, which is what? A strong oxidation. Why am I putting in excess? Because if the potassium dichromate is not in excess, this will be oxidized into the aldehyde. Are we together? So that's why we need to put it in excess. So I hope it is understood. So in conclusion, we can say that these are the answers we obtained from our solution. So they say in Roman 1, they say give the structure compound A and C. Compound A was what? Was propylamine, and compound C was butanamide. Now in Roman 2, they asked you to give the reaction, the reagent and the reaction condition which occur in Roman 1, Roman 2, Roman 3. We saw that in Roman 1 it was Hoffman degradation, in Roman 2 it was a strong reduction, and in Roman 3 was a strong oxidation which took place. Now in Roman 3 asks you to give the structure of D and E. So D, we say that what D was N-propyl ethanamide, and we say that what E was an alcohol. Now in Roman 4 they are asking you to give the functional group in C. So the functional group in C is CONH2 or CONH2, which is what the amide functional group. Now they are asking you to give a test for the amide functional group. How do we test for amide functional group? So to test for amide functional group, you simply react your unknown compound. So react unknown compound with cold nitrous acid. What will I obtain? I will obtain what? Bubbles of nitrogen gas. So that is one way in which I can confirm the presence of amide, or I can react my unknown compound with sodium hydroxide. If I react it with sodium hydroxide, I will have ammonia gas which will be released, which is what? A pyridine gas, which is basic, that is third red litmus paper to blue. So that is how I can test for my compound C. So this is all about the equation 2, which has to do with aliphatic synthetic code concerning nitrogenous compound. Alright, now we go to our question 3, which is our third form of synthetic code, in which we are having aromatic synthetic code. So the aromatic synthetic code has to do with what? Has to do with aromatic compound, that is compound containing the benzene ring. So let us see our question. So in our question, let us start from what? From the middle part. So either in our question, I am having my normal compound, which is C7H8. So let us first analyze this compound. Whenever you see that in a compound, I'm having the number of hydrogen is very close to the number of carbon atoms. Automatically, you know that there must be a benzene ring, that is when the numbers are close like this. Now, when we have a benzene ring, but generally the benzene ring is on C6H6. So it means that it's another molecule which started to. So we can say that this formula is representing what? C6H5 with CH3, which is what? Methyl benzene, which is methyl benzene or toluene, methyl benzene or toluene. So this methyl benzene can also be written in this form. Can also be written in this form. Are we together? So that is about what our center compound. But now we are seeing that this our compound is converted to two products. It's converted to two products, A and B, passing through the reagent Cl2 with aluminium chloride. Alright, so let us analyze it. Whenever you see chlorine in the presence of aluminium chloride, which is what a Lewis acid, what happens is that here you think about what? An electrophilic substitution reaction. So it means that what? I will not attack this small chain directly, no, but I will attack the ring directly due to the presence of this reagent. But now, if I attack the ring directly, in which position will I fix my chlorine? Now it depends on what? On this group that is there. So you need to know that what? CH3, which is an alkyl group, is what we call an electron activating or an electron donating group. This electron donating group will fix your upcoming compound either on the ortho or the para direction. So it means that this group are what we call ortho-para directory. Is it okay? Now other example of ortho-para directory, we have OH, which is also ortho-para. We have OCH3, which is also ortho-para, and we also have the halide group, which are ortho-para directory. Now, apart from this ortho-para directory, we also have what we call electron deactivating or electron withdrawing groups, which they themselves instead oriented into what? Meta direction. So example of such groups which orientate in the meta direction, we instead have what? The COOH. Are we together? We have the COCH3. So these people, they orientate instead on what? On the meta direction. So how do we easily identify them? So when we have an atom in which the atom next to him is less electronegative than him, it is surely what? An ortho-para directory group. Whereas when you see that the atom which is directly attached to the benzene ring, the atom next to him is more electronegative than him, it is surely what? The meta directory group. I hope all of you know about the ortho, the meta, and the para position of the benzene ring. If I am having my benzene ring, and I have a substituent here. If I have a substituent here, now the next person that will come, and if it fits itself at this position, we say it is about at the ortho position. If you come and fix itself at this position, we say you are about the meta position. But if you fix yourself here, we say that we are at the para position. So the same thing here, ortho and meta and para. So that is how we say ortho, meta, and para position. Alright, are we together? Alright. So it means that here, in this reaction, I will have two product, which is the ortho and the para product. So the ortho product I will have my ortho product, and I will also have what? And I will also have my para product. But now, As we are having two products in organic chemistry, there's always one which is the major product and the other one which is what a minor product. Now, in this our case, which one will be the major product and which one will be the minor product? So, in this our case, the major product is this one, and the minor product is this one. Why is this one the major product and why is this one the minor product? In organic chemistry, there is what we call steric hindrance, which is what an effect of an organic reaction. What is steric hindrance? It is what it is the prevention of the reactive side by bulky groups. You see that over here I am having a bulky group, which is a methyl group. So it will be very difficult for this chlorine to come and fix itself close to it. So we are going to reduce the number of chlorine which will be produced in this position. Whereas here I am having what? A position that is very free, so the chlorine is free to come and fix itself here. So that is why I'm going to produce more of this. Is okay, so here I'm having the major product and here I'm having the minor product due to what? Due to difference in steric hindrance. In this product I'm having what? More steric hindrance, whereas here I'm having what? Almost no steric hindrance. So that is about what? This is our first part of the equation. Hope this is understood. Now, in the next part of our synthetic route, we are seeing that we are having our toluene or our methyl benzene, which is converted to a compound D using what? Hydrogen or platinum catalyst at 200 degrees Celsius. So all of us have recognized this. It is almost our first reaction we saw in organic chemistry, which represents what? A hydrogenation, that is addition of hydrogen. But now in benzene, if we add hydrogen at a very high temperature, I will completely remove what? The saturation, unsaturation. I will create what? A saturated molecule. So here I will convert what my benzene ring into what? A cyclobenzene ring. So in this case, I will have this compound. I will have this compound, which is methyl cyclohexane, which is methyl cyclohexane, So when you perform the hydrogenation of a benzene ring, you will obtain what? Methyl cyclohexane. Alright. In the next part of my synthetic route, I am having my methyl benzene, which is converted to chloromethyl benzene, and they are asking me what the reagent and the reaction condition which is involved here. So we are seeing that what in such a reaction, it is not affecting the main ring, it is affecting only what these chain. Are we together? So here we are substituting a hydrogen with a chlorine in this chain, and it resembles what we call let us say a halogenation of an alkane. Now halogenation of an alkane, we generally put what? Chlorine in the presence of what? UV light to initiate what? A free radical substitution, in which we have seen earlier. So this is a free radical substitution which took place in the conversion of what? My methyl benzene to what? To my chloromethyl benzene. Now my chloromethyl benzene is converted to another reagent or another compound which is C7H7OH, and we put here asking the reagent and reaction condition. Now, before giving the reagent and reaction condition, you must first of all be able to identify which compound is it. So, as you are seeing, it automatically is a benzene ring that is there. Now, if there is a benzene and there is more carbon in it, there is a CH. So, what is likely the compound which is formed here? It is likely what? My benzene ring, and I will have what? A CH2, and I will have an OH, which is phenylmethanol. So I am having such a compound which is 4. So it means that all the reaction that is taking place, it has nothing to do with the ring, it has to do only with my chain, which is what my normal reaction that I know. So it means that if I'm replacing Cl with OH, it is what simply what in nucleophilic substitution reaction. So here I will need what? Under reflux. So this is what in nucleophilic substitution reaction. So I'll substitute my Cl with my OH. So that is what is happening in this my reaction. The next thing is that what? I am now converting what? My phenylmethanol. I will put a reagent which is concentrated sulfuric acid at 140 degrees Celsius to produce a compound E. Now, whenever we have seen that in this second branch we are dealing only with the chain, so the ring is not intervening. But now, whenever an alcohol is reacting with concentrated sulfuric acid at a lower temperature of 140 degrees Celsius, I will generally produce an ether. Whereas if the temperature was, so if I was having concentrated sulfuric acid but the temperature was instead 170 degrees Celsius, I will instead produce what an elimination reaction, which is an alkene. So take note about that. Okay, but now here I must have what an ester. So how is the ester formed? So generally, if you have an alcohol ROH, you put concentrated sulfuric acid and 140 degrees Celsius, the ester you are going to form is ROR. That is what you repeat this. So the same thing you are going to do, you are going to repeat this. So it means that my compound E will be benzene ring like this, a benzene ring with CH2, and I repeat the CH2 with a benzene ring. I repeat it. Is it okay? So this group like this is called benzene. It's called benzene group. So when I have what this ring, this CH2, we call it benzene. So I'm having two benzene and it is an ester. So the name of this compound is what? Dibenzene ester. So that is what is happening to what? So this my branch of my synthetic group. So I hope it is understood. Now we go to the second branch of our synthetic group, in which we are moving from what? My methyl benzene to such a compound. So as we analyze area, we are going to see that this compound automatically will be phenyl methanol. If you're very attentive, you have seen that word. We have not changed. It's the same thing, phenyl methanol. But now we are going to see that it passes through these two reagents, and of course it is normal, because if I am having toluene, and I pass it through chlorine in the presence of UV light, what will I obtain? I will substitute one hydrogen here, and I will finally obtain chloromethyl benzene. Now, if I perform a nucleophilic substitution by adding aqueous sodium hydroxide under reflux, I will finally have this my compound. So, which is logical. Are we together? Now, what is very interesting is that I am converting from this compound to this other compound. Now, I hope you are seeing that this compound is having an N, with CH. Now, I'm having an increase in the number of carbon. So, when you see such a compound, what are you going to think of? You see that it will be emitted, but the number of hydrogen have not increased, but nitrogen plus carbon have increased. So, if carbon and nitrogen have increased with the number of hydrogen which have not increased, it means that the CN have been added. So, it means that here we are actually converting from what? We are actually converting from this alcohol to what? Into this compound, which is phenylethanamide, which is phenylethanitrile, So as we are having this my compound, are we together? Now, how can I convert from here to here? So the first thing you need to know is that there is no direct conversion. So there is no direct conversion. So I'll perform through what I will turn around. So the first thing is that I will replace this OH with what? With bromine. So what will happen here is that I will perform a substitution reaction with bromine. So there is no direct conversion. So here I will pass through sodium bromide under reflux. So I will replace this OH with what? With this bromine. So finally I will have this my compound CH2 bromine. Now when I'm having this my compound, so this is the first reagent. Now when I have this my compound, the next thing is I will convert it now to this compound by adding potassium cyanide under reflux. Adding potassium cyanide under reflux. Adding potassium cyanide under reflux, I will replace the bromine now to it. So that is what is happening in this other conversion, because there is no direct conversion here. Now for the last conversion, it means that I am having my nitrile compound. And I want to convert my nitrile compound to carboxylic acid. So this one is a standard. So this one is a standard. Whenever you want to convert the nitrite functional group to the carboxylic acid functional group, you simply add acidified water and you warm it. You add acidified water and you warm it. So finally you have your organic compound that you form our equation and our solution. These are the answers we are able to obtain. So compound A is 2-chloromethylbenzene, compound B 4-chloromethylbenzene, compound D is methylchlorohexene. Compound B is the major product to explain the effect of steric trans. Now we give the reagent reaction condition for what? For the convention 1-3-1-5. Finally you give a compound of the structure of this compound, which was what? D-benzene ether. Now, next question, they are asking you the type of reaction mechanism that took place. We see what's the nucleophilic substitution mechanism. They are asking you to describe a simple test to test for the presence of chlorine in organic compound. To test for chlorine in organic compound, we simply follow what we call the Lazarine test. In the D part of the equation, they are asking you to test for chlorine. How do we test for chlorine? We say that was the Lazarine test, which is used to test for chlorine. So in this Lazarine test, you are going to take what portion of what of your sodium fusion test. You are going to add nitric acid followed by silver nitrate, a white precipitate of silver chloride with the presence of chlorine. And in the last part of the equation, they are asking you to define the reaction mechanism involved in the conversion. So the reaction mechanism here was a free radical substitution. We have defined it in the previous video. Same thing with the nucleophilic substitution reaction. So I think with that, you are having sufficient material to attack the GC concerning synthetic route. So I hope you have understood something concerning the synthetic route, and good luck for your exam. So we can comment for any question.